In this video, we will talk about Taylor and Maclaurin polynomials and series. In Calc 1, we learned linearization to approximate the y value for a function which was difficult to find using the tangent line approximation. So we saw we could use a point closer to the one that we're looking for, a nicer point closer to where we want to find the y value, and use the tangent line at that point to approximate the y value of a function. But as we move further away from the center, the accuracy of our approximation decreases because linear approximation or tangent line approximation does not take into account the rate at which derivative is changing. So there's a better way to approximate the functions, which is using Taylor and Maclaurin polynomial or Taylor or Maclaurin series. Higher the order of Taylor polynomial, better approximations we get for the function value. Taylor polynomial. So if f is a function with the derivative of all orders throughout some open interval containing x equals a, then the Taylor polynomial Tn for f centered at x equals a is written by Tnx equals f of a plus x minus a over 1 factorial f prime of a plus x minus a square over 2 factorial f double prime of a plus x minus a to the third power over 3 factorial f third derivative of a, and so on. And we can write the Taylor series thinking about the general nth term here. So would be summation n is equal to 0 to infinity nth derivative of f at point a over n factorial times x minus a to the nth power. Degree of Taylor polynomial is the highest exponent of x. And the order of Taylor polynomials, when you see T3, we are talking about the Taylor polynomial of order 3. So with the 3 in the foot, that's the order for the Taylor polynomial. The order of the Taylor polynomial is the highest derivative used to create Tn. Maclaurin polynomial. Maclaurin polynomial is the Taylor polynomial centered at a is equal to 0. When we write the Taylor polynomial at the center a is equal to 0, we get Maclaurin polynomial. So m and x can be written as f of 0 plus x over 1 factorial f prime of 0 plus x squared over 2 factorial f double prime of 0, and so on. And we can write the Maclaurin series by generalizing. So n is equal to 0 to infinity, nth derivative at 0 over n factorial times x to the power n. So we're replacing every single a by 0 in this function, in the Taylor polynomial. And that gives us Maclaurin polynomial. Now we're going to do some examples of finding the Taylor and Maclaurin polynomials. Now here, we are being asked to find the Taylor polynomial, but it is centered at 0, so it's also called Maclaurin polynomial. So this is also called Maclaurin polynomial because our center is at 0. Let's go ahead and approximate f of x is equal to e to the power x at x equals 0. We're gonna write the first 3 terms only for now. So we have f of x is equal to e to the power x. So let's first write down what is Taylor polynomial. Taylor polynomial is Taylor polynomial is Tnx equals f of a plus x minus a over 1 factorial. Okay, so Tnx, we want the order 3, so we'd say T3x is equal to f of a plus x minus a over 1 factorial f prime of a, x minus a over 1 factorial f prime of a plus x minus a square over 2 factorial f double prime of a. Because we want the third order, we will have to go up to third derivative. X minus a to the third power over 3 factorial and the third derivative of at point A. In our case, the point A is 0, so that should make a little easier. F of x is e to the power x, f prime of x is also e to the power x, f double prime of x is also e to the power x, f triple prime of x is also e to the power x. F of 0 is going to be 1, f prime of 0 would be also 1, f double prime of 0 would be also 1, f triple prime of 0 would be also 1. So all these derivatives are coming out to be 0. So a third order Taylor polynomial turns out to be f of a, which is going to be e to the 0 power, plus x minus a, the center a is 0, x over 1 factorial times the derivative, plus x squared over 2 factorial times the derivative, plus x3 over 3 factorial times the derivative, and so on. This is a Taylor polynomial or Maclaurin polynomial of the order 3, which is 1 plus x squared over 2 factorial plus x to the third over 3 factorial. If we were to write the nth order polynomial, or if we were to write the Taylor series for it, let's just see what t n x is going to be. If I continue and go on, it's going to be 1 plus x squared over 2 factorial. Although we were not asked to do it, but let's just see the pattern. X to the 5 over 5 factorial all the way up to x to the n over n factorial. And that's going to be my nth order Taylor polynomial. This is my nth order Taylor polynomial. If I were to express this as a summation, I would go t n x is equal to, or Taylor series can be expressed as, for e to the power x, Taylor series will be expressed as summation n is equal to 0 to infinity x to the power n over n factorial. So starting with n is equal to 0, when we plug n as 0, we would get x to the 0 power over 0 factorial. Remember, 0 factorial is equal to 1. Okay, see another example. Compute the Taylor polynomial T4 centered at a is equal to 3 for square root of x plus 1. Okay, so we are trying to figure out a polynomial which is centered at a is equal to 3 and the function is square root of x plus 1. So how do we find a Taylor polynomial for this function? We would have to use the Taylor formula that we saw earlier. It was t, and it's a fourth order, t4x would be f of a plus f prime of a into x minus a over 1 factorial plus f double prime of a into x minus a squared over 2 factorial. Doesn't matter, you can write the 2 underneath the whole thing or just under that term. F triple prime of a x minus a squared over 3 factorial plus f the fourth derivative of at a x minus a 4 power to the 4 factorial. Okay, so I need to figure this out, and it's going to be a lot of work, so it's good to stay organized, make a table. Let's go ahead and first think about what is f of a. My center a is 3 in this case. F of a would be, f of a is f of 3. What is f of 3 going to be? So for every single a, I'm going to plug a 3 in. I'm going to find the derivatives, and I'm going to be evaluating the derivatives at x equals 3. F of a is equal to f of 3. That's going to be square root of 3 plus 1, which is 2. F prime of a would be 1 over 2 square root of x plus 1. And that's going to be, so f prime of 3 would be 1 over 2 times square root of 2 would be 4. And then I have f double prime of a would be 1/2 x to the power negative 1/2, which would be negative 1/4 here. So I'd have negative 1/4, and then x plus 1 to the power 3/2. F prime at 3, f double prime at 3 would be negative 1 over 4. X is 3. We're evaluating the derivative at x equals 3. 3 plus 1 is 4. 4. Actually, I'm just going to leave this as, I'm not using the value a yet. I'm just finding the derivative in terms of x and then plugging in the value a. 4, square root of 4 is 2. 2 to the third power is 8, which is negative 1 over 32. And now I'm going to find the third derivative of x. This is going to be negative 1 over 4 times, would be 3/8. That would be 3/8. And it's going to be positive because we already have the negative in the front. And when we bring negative 3/2 in the front, it would become positive. And now I'm going to find the third derivative at 0.3. That would be 3 over 8. 3 plus 1 is 4 to the power of 5 halves. So that's square root of 4 raised to the 5th power. 3 over 8 times square root of 4 is 2. So use a calculator, and that's 4 to the power 5 over 2 times an 8. That would be 256. Now we're going to look at the fourth derivative. Again, for the fourth derivative, it's going to be negative. And instead of 3/8, it would be 15 over 16 x plus 1 to the power 7 halves. X to the power. Now, fourth derivative at x equals 3 is going to be negative 15 over 16. And then 4 to the power 7 halves. So square root of 4 is 2. 2 to the 7th power is 128. 128 times 16. That would be negative 15 over 2048. Okay, so here's all the derivatives we need. And I think we're ready to write the polynomial t for x. T for x in this case would be f of a, which is 2, plus f prime of a times x minus a. F prime of a is 1/4 times x minus 3. And then we have plus, actually it's going to be minus 1 over 32. So negative 1 over 32 x minus 3 to the second power, plus 3 over 256. Oh, we also have 3 over 256. That would be over n factorial also. Don't forget, we also have the n factorials in the denominator. So that's going to be first term. Second term will have 1 factorial. It doesn't matter. The next term will have a 2 in the denominator as well. So there's also a 2 here. And the third term will have a x minus 3 to the third power over 3 factorial, which is equal to 6. Plus, the next term is actually going to be negative. So minus 15 over 2048 times x minus 3 to the 4th power over, that's going to be 4 factorial. 4 factorial is 4 times 3 times 2, which is 24. Now, this is our Taylor polynomial for this function. We can go ahead and clean it up a little. Use a calculator to do the multiplications that are needed. 32 times 2 is 64. 256 times 6. That would be... now we can cancel the 256 times 2 because we can cancel the 3 and 6. So that would be 1 over 512 x minus 3 to the third power minus, canceling again, it would be 5 over 16, 384 x minus 3 to the 4th power. So that's our Taylor polynomial in this case, and the center for the Taylor polynomial for this problem was x equals 3. Next, we're going to compute the Taylor polynomial for natural log of x at a is equal to 1. So I'm looking for a Taylor polynomial Tn. So I'm looking for a general polynomial where I do have the nth term. That would be Tn. Okay, so let's see. We're going to write the nth term as well. So this is going to be f of Taylor polynomial Tn is equal to Tn of x. Let's just call it Tn is a function of x. It's going to be f of a plus f prime of a x minus a over 1 factorial plus f double prime of a x minus a to the second power over 2 factorial plus f triple prime of a x minus a to the third power over 3 factorial, and so on. So let's write first few terms and see how does this series look. F of a, so my derivative f of x is equal to, f of x is natural log of x. F of 1 would be natural log of 1, which is 0. F prime of x is 1 over x. F prime at 1 would be 1. F double prime of x is, this is x to the power negative 1. So negative 1 x to the second power. F double prime at point 1 would be negative 1 over 1. It would be just negative 1. And third derivative would be going to be positive 1 over x to the third. The third derivative also, I would have 1 here. So start with the zeroth. The very first term would be 0, and then it would be 1. Then it would be negative 1 over x. Oh, negative 1 over x squared. If I plug a 1 here, that's negative 1/2 actually. And if I plug a 1 here, 1 over x to the third, negative 1 over x squared, that would be, no, that's correct. Okay, the third derivative would be equal to 1 again. Now we're going to write the fourth derivative. Fourth derivative would be negative 1 over x to the power 4. So fourth derivative would be negative 1. Fifth derivative would be positive in this case, 1 over x to the fifth. So fifth derivative at 1 would be again positive 1. So we see the pattern. We're going from 0 to 1 to negative 1 to and so on. So let's go ahead and write the Taylor polynomial. Tn of x would be equal to f of a, which is 0, plus f prime of a, which is 1, times x minus a. So that would be 1 times x minus 1. And over 1 factorial, that doesn't really make any difference. And the next term would be f double prime of a, which is negative 1. So this is going to be a negative term. Negative 1, x minus 1 to the second power, divided by n factorial, which is going to be 2 factorial. So first term 0 factorial, 1 factorial, 2 factorial. And the next term we're going to have plus x minus 1 to the third power over 3 factorial, minus x minus 1 to the fourth power over 4 factorial, plus x minus 1 to the fifth power over 5 factorial, and so on. So the nth term looks like it would be negative 1 to the nth power, and then I have n minus 1, n minus 1, n minus, so in the first term I have 0 factorial, second term I have 1 factorial, so I do have n minus 1 factorial in the denominator. Negative 1 to the power n, x minus 1, x minus 1 to the power first term, second term, third term, n minus 1 over n minus 1 factorial. Looks like this is going to be my nth term in this case. So I'm going to be able to write infinite terms, as many as I want, all the way up to the nth term here. Okay, and that's my subsequent coefficient: 0, 1, negative 1/2, and then I have 1/3 factorial there. Okay, so that's going to be the nth Taylor polynomial for this problem. Now we're finding the third polynomial for sine of x at a equals pi over 4. Third Taylor polynomial for sine of x. Okay, so my function is sine of x, and we want to find the third Taylor polynomial. That would be T3 of x would be equal to f of a. This Taylor polynomial can be used to approximate the value of function at any point close to a. So f double prime of a, x minus a to the second power over 2 factorial, plus f third derivative of a, x minus a to the third power over 3 factorial. So that's going to be a Taylor polynomial of third order. Now let's see f of a. F of x is sine x. F of pi over 4 would be sine pi over 4, which is root 2 over 2. Root 2 over 2. Now f prime of x is cosine of x, and that's going to be again f prime of pi over 4 would be root 2 over 2. F double prime of x is going to be negative sine x. So second derivative would be negative root 2 over 2. And now I have the third derivative of x, which is going to be negative cosine x. So third derivative at pi over 4 is going to be negative root 2 over 2. Okay, so we're ready to write the third order Taylor polynomial, T3x. Taylor polynomial gives us a much better approximation than the linear approximation, because Taylor polynomial mimics your function much closely. It follows your function much closely. The higher the order of Taylor polynomial, more closer your approximation, better approximation you will get to the actual function. T3x would be f of a over 0 factorial. So f of pi over 4 is square root of 2 over 2 plus root 2 over 2 times x minus a. X minus a would be x minus pi over 4 plus root 2 over 2. Actually, this is going to be minus here. F double prime of a is a negative root 2 over 2. And then we also have 2 factorial, x minus pi over 4 squared. We have 2 factorial at the bottom, which is going to make it a 4 here. Going to make it a 4 because of the 2 factorial in the denominator. That's going to be a 4. And the next term will be negative again, root 2 over, we can have 3 factorial. 3 factorial is 6. 6 times 2 will be 12. X minus pi over 4 to the third power. So that's a third order Taylor polynomial for the function f of x is equal to sine of x at point x equals pi over 4. Next, we want to find the Maclaurin polynomial for f of x is equal to cos x. We know the Maclaurin polynomial is centered. Maclaurin polynomial is necessarily Taylor polynomial centered at 0. So Maclaurin polynomial would be f of 0 plus f prime of 0 x, f double prime of 0 x squared over 2 factorial, f triple prime of 0 x to the third over 3 factorial. All the a's become 0 in this case. The fourth derivative at 0, x to the fourth over 4 factorial. Fifth derivative at 0, x to the fifth over 5 factorial, and so on. Okay, so let's see, my f of x is, in this case, f of x is cosine of x. What's cosine of 0 going to be? Cosine of 0 is 1. First derivative, f prime of x. Derivative of cos x is negative sine x. F prime of 0 would be negative sine of 0, which is 0. F double prime of x would be negative cosine of x. And f double prime at 0 would be cosine of 0 would be negative 1 here. Now we have the third derivative. Derivative of negative cosine x would be positive sine x now. So positive sine x. And the third derivative at point 0, sine of 0 is 0. Now we have the fourth derivative of x, which is going to be cosine of x. And the fourth derivative at 0 would be 1. Fourth derivative at 0 would be 1. So let's write down the fourth order Taylor polynomial, and then we can go ahead and think about, so we're writing the T4 here, or M4. So write M4. We're just going to write M4 and see the pattern, what's happening to the terms. So I would have f of 0, which is going to be, f of 0 is going to be, M4x is going to be here, 1. And the next term is actually going to become 0. So I'm going to have this term become 0 because f prime of 0 is 0. And then the next term would be negative x squared over 2 factorial, x squared over 2 factorial. And then the next term again will become the next term, the third derivative term will again become 0 because f triple prime of 0 is 0. Now I'm going to have the fourth term where I have 1 or x to the fourth over 4 factorial, and so on. So if you look carefully for this series, that I'm going to have all the second, I do have a first term, I don't have a second term, I don't have a fourth term. So second term is gone, fourth term is gone, the sixth term is going to be gone, and so on. Second term, fourth term, and sixth term, and so on are gone. All the even terms will be gone in this case. So this polynomial is only going to have the odd terms in here. All the even terms will become 0 eventually for this polynomial. And we can express it in this form: -1 to the power n, x to the power 2n over 2n factorial. So for cosine x, we can express the Maclaurin polynomial as -1 to the power n, x to the power 2n over 2n factorial. So summation n is equal to 0 to infinity, -1 to the power n, x to the power 2n over 2n factorial. So we can express the general mn x using this. So this is your Maclaurin series with infinite terms. Maclaurin series with infinite terms. So we first wrote the one with the 4 terms, and then we wrote Maclaurin series with infinite terms. Maclaurin series with infinite terms for cosine of x. So for f of x is equal to cosine of x, we just wrote the Maclaurin series.